We are going to take the integral of 2 times t to the 5th over the square root of t squared plus 2. Now, there's a lot packed into this innocent-looking problem, so let's get started. So the denominator, t squared plus 2, we really don't like this 2 here. We would much rather prefer a 1. So we are going to get rid of that. So let's see if we can rearrange this square root of t squared plus 2 in some other way so that we can get our desired result. So if we factor out a 2 inside this square root, then what we are going to get is t squared over 2 plus 1. And right now, if we were to bring this 2 into this t squared, then what we are going to get is 2 times t over square root of 2 all squared plus 1. So if we were to just bring this root 2 out as a product of two square roots, then what we have is root 2 times t over root 2 squared plus 1. Now, these steps may seem sort of arbitrary, but they're not. They're to get this t prepared for a substitution, because we want our denominator to look exactly like u squared plus 1, where we can substitute this for u. We really don't like this 2 over here, so we're just going to take it out. So I'm just going to go over these steps one more time. We've just factored out a 2 in our initial step, and we've just brought our 2 into this square. So t over root 2 squared is just t squared over 2. And in our final step, we've just multiplied the two square roots together, and we've taken the reverse of that, so we have these two taken apart. So we've took this root 2 out of this radical. So now we can rewrite our integral as the integral of 2 t to the 5th dt over, now this bottom is just what we wrote over here, so it's root 2 times the square root of t over root 2 all squared plus 1. Now this is all under the radical over here. I'll just make it longer so that it'll fit everything. So now we want to choose something to substitute for t over root 2, and we want this to be able to cancel out. So we would need to use a trigonometric substitution for this problem. So let's write down our known trigonometric identities. So we can write our two important ones: sine squared, let's call it theta, plus cos squared of theta equals 1. And if we divide everything by cos, we get tan squared of theta plus 1 equals secant squared of theta. So now our question is whether to use sine, cosine, tangent, or secant. So if we have t over root 2 squared plus 1 underneath a square root, we want the result to be able to be squared. So if we take a look at what we have under here, we have this thing squared plus 1. Well, the expression most similar to that is this right over here. We have this thing squared, tan squared, plus 1. So our this thing squared should probably be tangent, because it is most similar to our expression here. Our ultimate goal is to convert this into secant squared, and then we can take the square root of that, and then it'll just be secant. So we are right now going to do that substitution. So we are going to have t over the square root of 2 equal tangent theta. So if we do this, then we can rewrite our integral using this new theta instead of t. So first, we need to take the derivative of this. So if we take the derivative of the left-hand side, we get 1 over root 2 dt, and that's going to be equal to the derivative of the right-hand side, which is secant squared theta d theta. So now we can rewrite our integral in terms of this new variable theta instead of t. So let's go on ahead and do that. So right now we have, let's use a different color here. Let's use this orangey yellow. So we have this 1 over root 2 dt. So that is right on over here, 1 over root 2 dt. And that can be replaced by secant squared theta d theta. And we also have our t over root 2. So our t over root 2 can be replaced by our tangent theta. So this t over root 2 inside this bracket over here can be replaced by tangent theta. Now what about our t to the 5th? Well, if we solve for t, then what we get here is t equals root 2 tan theta. So we've just rearranged this equation up here so that the root 2 is now on the theta side. So now all of the t's can be replaced by root 2 tan theta. So now everything seems set. Let's go on and do our substitution. So we have our 2. We have our t to the 5th. So this is just going to be root 2 tan theta to the 5th. And we are going to have our dt over 2. So the dt over root 2, root 2, not 2. Our dt over root 2 is going to be equal to secant squared theta d theta. So let's write that down here. Secant squared theta d theta. And now onto our radical. So our radical in the denominator is going to be the square root of tan theta squared, because t over root 2 is going to be replaced by tan theta. So we have tan squared theta plus 1. So that was a lot to take in. So if you want right now, you can just pause and take a look at all the substitutions that we did. Hopefully they make sense. So right now we've taken our integral in terms of t and turned it into an integral in terms of theta. So now what we want to do is simplify this bottom part over here. So we want to write tan squared theta plus 1. Instead of tan squared theta plus 1, we are going to write it in terms of secant. So it's going to be root secant squared. So let me just rewrite everything over here. We have the integral. On the bottom, it's going to be the square root of tan squared plus 1, which is secant squared theta. So the square root of secant squared is just going to be secant theta. So our denominator, our entire denominator has been simplified to secant theta. So on the numerator, let's just take everything in this bracket to the power of 5. So we have our 2 times the square root of 2 to the power of 5. So the square root of 2 to the power of 5 multiplied by tan theta to the power of 5 multiplied by secant squared theta d theta. Secant squared theta d theta. So now notice how 2 to the power of 5 underneath a square root, well, 2 of those 2's can come out. I know that's kind of confusing, so let me just write it in another way over here. So 2 to the power of 5 equals the square root of, let's see, we'll call this 16 times 2, because 16 is 2 to the power of 4 times 2, so that's 2 to the power of 5. And this is equal to 4 root 2. So we can plug that into our 2 to the power of 5 underneath the square root over there. So we are going to rewrite our integral as 2 times 4 root 2 tangent to the 5th theta. And now we have secant squared theta over secant theta. So one of the secant thetas on the numerator can cancel out with the one on the bottom. So all we get is secant theta d theta. So right now, I think it's worthwhile to just take a moment to take it all in. And I'm just going to keep simplifying this. So here we have 8. So 2 times 4 is 8. So I'm actually going to take this outside of the integral. So 8 root 2. So 2 times 4 root 2 is 8 root 2. The integral of tan to the 5 of theta secant theta d theta. So we've simplified our integral in terms of t into this integral in terms of theta. Now, this may not seem much more simple than the original integral, but trust me, it is. This is the way to compute it. So now we're just going to go on to a new page, and let's see, we'll hide this one and keep our original one. So we know that this integral is equal to what we've kept here at the bottom. So this is 8 root 2 tan to the 5th theta secant theta d theta. Now notice how tangent theta is to an odd power. So if it's to an odd power, we can express, for example, tan theta to the 4th in terms of secant theta. And then we can use integration by substitution to figure out what our integral will be. So let's, instead of writing tan 5th theta, let's just rewrite this as this. So we have our constant in front, and we have tan to the 4th of theta, tan to the 1 of theta, and secant theta d theta. So let's consider the derivative of secant theta. So d over d theta of secant theta, so that's a secant theta, it's not a good C, secant theta is going to be equal to secant theta tan theta. So we have our secant theta tan theta right here. So all we have to do is convert this tan to the 4th theta into secant theta. So let's convert this tan 4th theta to tan squares. So to do that, we can just have this be tan squared theta, all of that squared. And here we have secant theta tan theta. I'm just reversing this order here, but that's okay. And remember our identity. So our identity tells us that secant squared theta equals 1 plus tangent squared theta. So if we solve for tangent squared theta, we get secant squared theta minus 1. So now we can rewrite this as 8 root 2, the integral of secant squared theta minus 1 squared times secant theta tan theta. So secant theta tan theta, and don't forget our d theta. I forgot it up here. The d theta is very important. So now we have everything in terms of secant theta, and now we have a secant theta tan theta d theta, which we can use for integration by substitution. So now let's have another variable. Let's just call this w. So w is going to be equal to secant theta, and dw is going to be equal to secant theta tan theta d theta. So secant theta tan theta d theta. And notice how these are the same. So this secant theta tan theta d theta is the same as this. So that can be replaced by dw. This secant theta can be replaced by w as well. So now what we have is our integral in terms of w. So here we have 8 square root of 2, the integral of w. So we'll just expand this this square over here. So we'll have w to the 4th minus 2w squared plus 1. So all I did was just expand this in terms of w. And here I'm just going to replace secant theta tan theta d theta with dw. So now we have this integral in terms of w. So now we can finally take antiderivatives easily using the reverse power rule. So we have 8 root 2. The antiderivative of w to the 4th is 1 over 5 w to the 5th. And the antiderivative of 2w squared is going to be 2/3 w cubed. And the antiderivative of 1 is just w. And don't forget our constant of integration. So now what we want to do is express our answer in terms of t. But first, w is in terms of secant theta. So let's write everything in terms of secant theta. So we're going to have 8 square root of 2, 1/5 of secant theta to the 5th minus 2/3 secant theta to the 3rd plus secant theta plus c. And now let's try to remember what secant theta was. So if we go back to our original page over here, we defined secant theta as we defined our variable theta in terms of tan theta. So we know that tan theta is t over root 2. So let's just rewrite that. So we have, let's just write that down here. We have tan theta equals t over root 2. So let's go back to our page again so we don't see all this mess. So we have tan theta equals t over root 2. I don't think we need that either. So we have tan theta equals t over root 2. So if we were to draw a diagram of this, what would that look like? So we need let's see, where is our previous work? Here's our previous work. So, if we draw a diagram of this, then this would look like, let's see, this would look like this. So if we draw a triangle where theta is the angle here, then tangent of theta is opposite over adjacent. So SOHCAHTOA, tangent theta, is opposite over adjacent. Well, opposite is going to be t. So we have our t here. And our adjacent is going to be the square root of 2. So from this tangent theta equals t over root 2, we have this triangle. Tangent theta equals opposite, which is t, over adjacent, which is root 2. And by the Pythagorean theorem, we can solve for the hypotenuse, which is a squared plus b squared. So it's 2 plus t squared. Now we have our integrals in terms of secant theta. Well, what's secant? Secant is 1 over cosine. So cosine in SOHCAHTOA is adjacent over hypotenuse. So the secant would be the hypotenuse over the adjacent. So let's just write that down. So secant theta is going to be equal to the hypotenuse, which is 2 plus t squared, over this adjacent, which is root 2. So every time we have a secant theta, we can replace it by 2 plus t squared over 2, all under the square root. So what we have as our final answer is going to be 8 times the square root of 2 multiplied by 1/5 secant theta to the 5th. So secant theta is just root 2 plus t squared over root 2, this to the 5th, minus 2/3 of secant theta again. So this is going to give us this secant theta expression again, but this time to the power of 3. And we're going to get it one more time, but this time only to the power of 1. And this is the final answer to this indefinite integral plus c. So through trig substitutions, through integration by substitution, through drawing triangles, we have determined that the integral of this function up here, 2 times t to the 5th over the square root of t squared plus 2, is equal to this expression down here. Now you can go tell your calc teacher that you love them.